Welcome to this explainer. Okay, let's dive right into a seriously bizarre mystery from the final frontier. Imagine you're floating in a weightless environment, just unpacking some daily supplies, and you unscrew a simple piece of hardware. Well, what happens next ends up baffling scientists, launching a 10-year classified government secret, and revealing an invisible mathematical law that governs literally everything from the stuff sitting on your desk right now, all the way to dying stars out in deep space.
So if you were to spin an object in zero gravity, you'd probably think it would just spin perfectly forever, right? I mean, Isaac Newton taught us that an object in motion stays in motion. If you just flick a spinning object in the vacuum of space, your intuition totally tells you it should just maintain a smooth, continuous rotation indefinitely. But, physics has a pretty mind-bending surprise in store for us here. Picture this. It's 1985, aboard the Soviet Salyut 7 space station, and a highly experienced cosmonaut named Vladimir Dzhanibekov is unpacking some cargo. These payloads were strapped down by long threaded rods and wing nuts. To speed up what was a pretty tedious process, he just taps the wing of a nut to make it spin rapidly, so it would essentially unscrew itself. The nut leaves the rod, flies through the cabin, and then, after traveling about 42 centimeters in this perfectly stable spin, the nut suddenly and violently does a 180-degree round-off backflip in midair. It just completely reversed its orientation while still flying forward. A few moments later, it flipped right back. It literally looked like magic.
Now, here's the really wild part. Soviet authorities were so alarmed by this discovery that they actually classified it as a state secret for a full 10 years. I mean, to a casual observer, a flipping piece of hardware just seems like a quirky little anomaly of zero gravity. But to the scientists analyzing Dzhanibekov's report, this bizarre physical behavior set off absolute alarm bells.
They kept it hidden because they were absolutely terrified this newly observed Dzhanibekov effect meant our very own planet might violently flip 180 degrees. Think about it. If a spinning object in space can just spontaneously flip its axis without any external force acting on it, they reasoned, what on earth is stopping the Earth itself from doing the exact same thing? A massive new hypothesis emerged that the Earth might regularly perform these devastating flips every 12,000 years. That would be an apocalyptic doomsday scenario.
Let's bring this cosmic mystery back down to Earth for a second to see how it actually works, because you don't even need to be in space to test this. This phenomenon is commonly known as the tennis racket theorem. If you grab a tennis racket by its handle and toss it spinning into the air, it rotates perfectly stably. But if you hold the racket with its face horizontal and throw it up so it spins end over end across its middle axis, it won't spin cleanly. It will randomly flip a half rotation mid-flight so the opposite face of the racket lands in your hand. You can literally try it right now with your smartphone. Actually, maybe use a calculator so you don't break your phone. Getting it to spin cleanly on that middle axis is practically impossible.
And this brilliantly shows us how the underlying mechanics work. Every rigid object has three distinct principal axes of inertia. Just think of them as length, width, and depth. The first is the easiest axis to spin, where the mass is packed closest to the center, like the handle of our tennis racket. The second is the hardest axis, where the mass is spread furthest out. Spinning an object on either its easiest or its hardest axis is perfectly stable. But that third option, spinning on that middle intermediate axis, that is inherently chaotic and unstable. But here is the craziest part of the whole shebang. This 1985 space anomaly was actually predicted over 200 years earlier. Enter the legendary mathematician Leonhard Euler, who published the exact equations for rigid body dynamics way back in 1758. So while the Soviet space program thought they had stumbled upon a terrifying brand new physical law, they were really just watching Euler's 18th century equations playing out in perfect weightless conditions. To really understand why the math forces this weird flip, we have to talk about kinetic energy. When an object spins, both its angular momentum and its kinetic energy absolutely must be conserved. If you spin an object on its lightest axis, it's operating at the absolute highest possible kinetic energy for that momentum. Spin it on its heaviest axis, and it operates at the absolute lowest kinetic energy. In both of those extreme states, the object literally has nowhere else to go without breaking the fundamental laws of physics. It can't magically gain or lose energy out of thin air, so it just stays perfectly stable. But that middle axis, things get really weird there. Because it represents a middle energy state, it isn't locked into a maximum or a minimum limit. The energy is basically stuck in this vulnerable sweet spot. If there is even the tiniest microperturbation, literally just a fraction of a millimeter off-center, centrifugal effects are going to cause the components of momentum to wildly shift.
the object is mathematically forced to physically flip over to reorient itself. It'll stabilize temporarily, but then the instability builds right back up and it flips all over again. So back to that whole Soviet doomsday panic. You can breathe a huge sigh of relief right now because the Earth is completely 100% safe from the Dzhanibekov effect. Our planet is essentially an oblate spheroid, which just means it bulges a bit at the equator. And because of this shape, the Earth actually rotates around its axis of maximal moment of inertia. That's its lowest possible energy state. As we just learned, this extreme state is incredibly stable, meaning our planet is definitely not going to spontaneously tumble 180 degrees anytime soon. Let's zoom out for a second and just look at the real-world consequences of this math across history. Because the intermediate axis theorem has evolved from just pure theory on paper in 1758 to a massive aerospace engineering headache in the 1950s, to a classified space mystery in the 80s, and finally, into cutting-edge future tech. Actually, before Dzhanibekov ever flew, American scientists learned about this instability the hard way. Back in 1958, the United States launched its very first satellite, Explorer 1. They designed it to spin like a bullet on its long, lightest axis. The problem? It wasn't a perfectly rigid body. It had flexible structural elements, like these long whip antennas. The flexing caused energy to dissipate, and because it was losing energy, it simply couldn't maintain that high-energy, stable spin. The satellite began tumbling completely out of control until it settled into a flat end-over-end spin, which was its lowest energy state. Now let's scale this concept up from a little metal satellite to, well, deep space. Astrophysicists are actively studying highly dense dying stars known as triaxial neutron stars, or magnetars. If one of these massive celestial bodies happens to be rotating around its second principal axis, it will experience this exact same Dzhanibekov flip. But when a star flips, it is incredibly violent. That sudden shift creates immense Euler forces that literally physically tear at the star's crust, triggering massive X-ray bursts and giant fireballs that shoot across the universe. Think about that. A flipping wingnut and a blazing dying star are controlled by the exact same math. Looking forward, aerospace engineers are actually trying to turn this physics glitch into a feature. Researchers are proposing designs for morphing spacecraft that have internal masses capable of shifting mid-flight. By intentionally changing their own center of gravity, they can turn the Dzhanibekov instability on. That allows the spacecraft to effortlessly perform a 180-degree flip just to observe something behind them. Once they're flipped, they shift their mass back to switch the instability off, and they return to a perfectly stable spin without burning a single drop of fuel. How cool is that? It really leaves you wondering, doesn't it? We started with a cosmonaut just playing with a wingnut, and we ended up examining the violent, crust-tearing deaths of distant stars. When everyday items like a tennis racket and giant celestial bodies follow the exact same hidden rules, what other invisible mathematical forces are secretly puppeteering the cosmos around us? Definitely think about that the next time you flip an object in the air, and I'll catch you in the next explainer.